Proxima Centauri is a killer disguised as a neighbor. 4.2 light-years away, the closest star to our Sun sits quietly in the southern sky, invisible to the naked eye, and surrounded by planets we once hoped might be habitable. That hope is dying, and the more we look at Proxima Centauri, the more we realize that this little red dwarf doesn't just fail to support life. It actively destroys the conditions needed for life to exist. We've known about Proxima Centauri since 1915, when Scottish astronomer Robert Innes identified it as the nearest star to our solar system. For decades, it was a footnote, a dim ember on the edge of the Alpha Centauri system, too faint to matter. Then, in August 2016, a team of 31 scientists led by Guillaume Anglada-Escudé confirmed something remarkable. Proxima Centauri has a planet, an Earth-mass world sitting right inside its habitable zone. They called it Proxima Centauri B. The discovery ignited imaginations. Our closest stellar neighbor, hosting a rocky planet where liquid water could theoretically pool on the surface. If you were writing a script for humanity's first interstellar destination, you couldn't have cast a better star. Except that star is trying to kill everything around it. Proxima Centauri is a red dwarf, a class of star with roughly 1/8 the mass of our Sun. Red dwarfs are by far the most common type of star in the Milky Way, making up about 75% of the entire stellar population. They burn through their hydrogen fuel slowly, almost miserly, which means they can live for trillions of years. Our Sun will burn out in about 5 billion years. Proxima Centauri will still be glowing 4 trillion years from now. That sounds encouraging for life. A long-lived star means a long window of opportunity for biology to emerge, evolve, and grow complex. The problem is what Proxima Centauri does while it's alive. Red dwarfs are dim. Proxima Centauri emits only about 0.17% of the Sun's total energy. Because it's so faint, its habitable zone, the orbital distance where temperatures allow liquid water, sits extremely close to the star. Proxima B orbits at a distance of roughly 7.5 million kilometers. To put that in context, Mercury orbits the Sun at about 58 million kilometers, nearly 8 times farther out. Proxima B is practically hugging its star. That closeness creates the first cascade of problems. A planet orbiting that tightly is almost certainly tidally locked. One hemisphere permanently faces the star, baked in perpetual red daylight. The other hemisphere faces away, locked in endless night. The temperature difference between the two sides could exceed 400 degrees Celsius. If you were born on the dark side of Proxima B, you would live and die without ever seeing your own star. If you stepped onto the day side, you'd face relentless irradiation from a star that, despite its small size, has a very short temper. Some researchers have argued that a thick enough atmosphere could redistribute heat between the two hemispheres, creating a temperate band along the twilight zone where conditions might be tolerable. That's a reasonable idea in theory. In practice, it requires the planet to still have an atmosphere. And that's where Proxima Centauri's real character emerges. Proxima Centauri is a flare star. Its magnetic field, generated by convection currents churning through its fully convective interior, is tangled and volatile. When those magnetic field lines twist, cross, and snap, the star erupts. Not occasionally, like our Sun during a solar maximum. Constantly. In March 2016, the same year Proxima B was confirmed, the EveryScope telescope array caught Proxima Centauri throwing a tantrum that astronomers hadn't anticipated. The star's brightness surged by a factor of 68. A dim, invisible speck became, for a few fleeting seconds, bright enough to see with the naked eye from a dark site. This was the first superflare ever observed from Proxima Centauri, and it released a total energy of roughly 10 to the power of 33.5 ergs, about 10 times more powerful than any previously detected flare from the star. Ward Howard, the graduate student at the University of North Carolina who led the analysis, and his colleagues, ran the numbers on what this meant for Proxima B. The ultraviolet radiation from that single superflare reached the planet's surface with roughly 100 times the intensity needed to kill the hardiest known UV-resistant microorganisms on Earth. 100 times the lethal dose from one flare, lasting less than a minute. A single event like that, even if it happened once a decade, would be devastating. Proxima Centauri fires off superflares roughly 5 times per year. The Everyscope team modeled the cumulative photochemical effects of that flare rate on an Earth-like atmosphere around Proxima B. Within 5 years of sustained superflare bombardment, 90% of the planet's ozone layer would be gone. Complete destruction of the ozone would follow within a geologically short time frame. Without ozone, every subsequent flare's ultraviolet radiation would slam directly into the surface, unfiltered. 3 years after that first observation, things got worse. On May 1, 2019, a team led by astrophysicist Meredith McGregor at the University of Colorado Boulder was running a coordinated observation campaign. 9 different telescopes pointed at Proxima Centauri simultaneously, spanning radio wavelengths to ultraviolet. 40 hours of total observation time spread over several months. During that window, Proxima Centauri unleashed the largest flare ever recorded from the star. It lasted 7 seconds. In those 7 seconds, the star's ultraviolet brightness jumped by a factor of 14,000. The flare was roughly 100 times more powerful than anything our sun has ever produced. 5 of the 9 telescopes caught it, delivering the first multi-wavelength portrait of a stellar flare from any star other than our own. The flare also revealed something unexpected. It generated a massive spike in millimeter wavelength radio emission, a type of radiation astronomers hadn't previously known that stellar flares could produce. The millimeter and ultraviolet signals were tightly correlated, rising and falling in lockstep. That tight coupling hinted at underlying physics that models at the time couldn't fully explain. McGregor's summary was blunt. Proxima Centauri's planets are getting hit by something like this not once in a century, but at least once a day, if not several times a day. And on the question of habitability, a human being on this planet would have a bad time. Flares, though, are only one weapon in Proxima Centauri's arsenal. Between flares, the star drives a constant stellar wind, a stream of charged particles flowing outward from its surface. Our sun produces a stellar wind too, the same wind that pushes comet tails away from the sun and occasionally triggers auroras on Earth. Earth survives this wind because we orbit 150 million kilometers away, and because our planet generates a robust magnetic field, a shield that deflects most of the incoming particles around us. Proxima B doesn't have those advantages. Sitting 20 times closer to its star than Earth sits to the sun, the stellar wind pressure at Proxima B's orbit is estimated to be about 10,000 times greater than the solar wind pressure at Earth. The wind itself is likely 10 to 1,000 times denser, depending on where Proxima Centauri is in its 7-year magnetic activity cycle. And because Proxima B is probably tidally locked and rotates slowly, if it rotates at all, it may lack the internal dynamo needed to generate a protective magnetic field. Without that shield, the stellar wind doesn't just push against the planet. It reaches directly into whatever atmosphere exists and rips molecules away. Hydrogen gets heated by X-ray and ultraviolet radiation until it escapes the planet's gravity entirely, dragging heavier elements like oxygen and nitrogen with it. Over billions of years, this process can strip a planet bare. Proxima B receives 10 to 60 times more X-ray and extreme ultraviolet radiation than Earth does. Over its lifetime, it may have absorbed 7 to 16 times Earth's cumulative dose. Computer models suggest that even with a magnetic field as strong as Earth's, the atmospheric erosion from stellar wind alone, not counting the flares, would prevent Proxima B from holding on to an atmosphere long enough for biology to take hold. The evolution of life requires billions of years of stability. Proxima Centauri offers the opposite. There's another cruel twist built into the physics of red dwarf stars. Early in their lives, before they settle onto the main sequence, red dwarfs go through a pre-main sequence phase where they're significantly brighter and hotter than they will be in maturity. During this phase, which can last hundreds of millions of years, the the habitable zone sits much farther out from the star than it eventually will. A planet like Proxima B, which now orbits inside the mature habitable zone, would have spent those formative hundreds of millions of years much too close to a much brighter star. Any water on the surface would have been baked off before conditions ever cooled enough for it to be liquid. The planet got cooked before the oven reached its normal temperature. And Proxima B isn't the only victim. In February 2022, astronomers using the Espresso instrument on the Very Large Telescope in Chile announced the discovery of Proxima D, a third planet in the system. Proxima D is tiny, roughly 1/4 the mass of Earth, about twice the mass of Mars, making it one of the lightest exoplanets ever detected through radio velocity measurements. The gravitational tug it exerts on its star is so faint that Proxima Centauri wobbles back and forth at just 40 centimeters per second in response. Detecting that signal was a feat of instrumental precision. Proxima D orbits even closer to the star than Proxima B does, completing a full lap every 5.1 days at a distance of about 4 million kilometers. That puts it well inside the inner edge of the habitable zone. Its equilibrium temperature likely reaches around 87 degrees Celsius, too hot for liquid water even under ideal atmospheric conditions. And of course, it faces the same punishing flare environment as its sibling, only closer to the source. If Proxima B is standing too near a bonfire, Proxima D has its hands in the flames. Then there's the disputed third member, Proxima C, a candidate super-Earth roughly 6 times the mass of our planet, orbiting far out at about 1.5 astronomical units, with a period of 5.2 years. Ironically, at that distance, Proxima C may experience something closer to Earth-like stellar wind conditions. Simulations published in 2020 by a team including astronomers from the Harvard-Smithsonian Center for Astrophysics found that the dynamic pressure of the stellar wind at Proxima C's orbit is comparable to what Earth receives from the Sun. But Proxima C sits far outside the habitable zone, where temperatures hover around -234 degrees Celsius. The one planet that might survive the wind is too cold for liquid water. The one planet warm enough for water can't survive the wind. The system reads like a trap designed by someone who understood the rules of habitability and then set out to violate every single one. So where does this leave us? Not every scientist has given up on Proxima B. Some have proposed scenarios where the planet formed farther out and migrated inward after the violent early period, potentially arriving in the habitable zone with a fresh supply of volatile compounds, including water. Others have suggested that a very thick, carbon dioxide-rich atmosphere might prove resilient enough to withstand the flaring, that on a world denser and more volcanically active than Earth, outgassing could replenish what the stellar wind strips away. And then there's the question of subsurface life. Even if the surface of Proxima B is a sterilized, atmosphere-free wasteland, liquid water could theoretically exist underground or beneath a frozen crust, shielded from radiation. Something like the subsurface oceans we suspect exist on Europa or Enceladus in our own solar system. Life that never sees the surface would be invisible to our telescopes, but it could exist. These are not irrational hopes. They are, however, hopes that require a long chain of favorable assumptions, each one compensating for a fundamental hostility. The broader implications reach far beyond one planet. Red dwarfs account for roughly 3/4 of all the stars in the Milky Way. They host more rocky planets in habitable zones than any other type of star. Tens of billions of these worlds are estimated to exist in our galaxy alone. For years, that statistic was a cause for optimism. So many opportunities, so many potential Earths. The work on Proxima Centauri is systematically deflating that optimism. If the most common type of star in the universe is also the most hostile to the atmospheres of nearby planets, then the galaxy's most abundant real estate may be uninhabitable. Recent research reinforces this concern from multiple angles. James Webb Space Telescope observations of the TRAPPIST-1 system, another red dwarf with a celebrated family of Earth-sized planets, found that 2 of its innermost worlds appear to be bare rocks with no detectable atmosphere at all. The pattern is holding. Red dwarf planets in tight orbits are getting stripped, and the evidence is accumulating faster than the counterarguments. In 2025, a team used ALMA to build the first comprehensive flare frequency distribution for Proxima Centauri, based on 463 detected millimeter wavelength flares. That number alone tells you something. 463 flares detected in a finite window of observation. The distribution followed a power law. Weaker flares are far more common, but the powerful ones happen with enough regularity to be devastating. The cumulative effect is a planet under perpetual bombardment, a world where the radiation environment never stabilizes long enough for an atmosphere to recover, let alone for chemistry to become biology. What makes this star particularly frustrating for astronomers is that it is, in every other respect, perfect. It's close enough to study in extraordinary detail. Its planets are confirmed and characterized. Its habitable zone is well defined. The instruments exist to probe its atmosphere, its flare behavior, its wind. Proxima Centauri is the laboratory for understanding whether red dwarf systems can support life. And the laboratory keeps returning the same result. James Webb Space Telescope observations and upcoming instruments like the Extremely Large Telescope, expected around 2028, may eventually tell us whether Proxima B retains any atmosphere at all. If it does, the spectral lines will reveal its composition and history. If it doesn't, that absence will be its own kind of answer, not just for Proxima B, but for every rocky planet orbiting too close to a red dwarf anywhere in the galaxy. Proxima Centauri will keep burning for 4 trillion years. Long after our sun has swollen into a red giant and collapsed into a white dwarf, long after the inner solar system has been swallowed and spat out as a planetary nebula, this little red star will still be there, still flaring, still lashing its planets with radiation, still glowing too faintly for anyone to see with the naked eye, unless they happen to catch it mid-tantrum. We named it Proxima because it is near, and it is. 4.2 light-years is nothing, astronomically. Close enough that we can study its planets in detail, close enough that projects like Breakthrough Starshot have seriously proposed sending tiny spacecraft there within a human lifetime. Proxima is near, and it is knowable, and it is one of the most comprehensively studied stars in the sky. What we've learned is that proximity is not the same as hospitality. The closest star to our sun is not a beacon. It's a warning, a lesson in what the universe's most common type of star does to the worlds it keeps closest. And if the lesson holds across the galaxy, the search for life may need to look past the stars we can see most easily, toward quieter suns, farther away, where planets can hold their air long enough for something to breathe it. And that's it for this video. Thanks for watching, and I'll see you in the next one.